Okay, so we're going to talk today about exponential growth, and this will bring us into a territory that we'll be fully exploring next week, which is that of word problems, right? Word problems, you're given a sentence or a few sentences describing a problem, and you're supposed to figure out the math. Okay, so that is a problem in and of itself, to interpret words and turn them into equations. We're going to start today, and we're going to continue with that on Friday. So we're going to start with this idea of exponential growth, and to point out how it can be a little bit counterintuitive, exponential growth. Let me show you a problem. Suppose that you have a bottle that's full of sugar. Okay, and suppose that inside of that sugar you put one bacterium. So bacteria, you know, bacteria, right? So this bacterium is very happy in this sugar medium, and it starts growing. And you know, bacteria, the way they grow is they divide it into two, right? So let's say that this bacterium divides into two after, I don't know, let's say after 1 minute. And what happens after 2 minutes? How many bacteria do you have? Everybody agrees we have 4, not 3, right? Because each of them is doing their own thing and is dividing. So after 1 minute more, you have 4 bacteria. 1 minute. Okay, now suppose that after 60 minutes, the bottle is full. So basically, I'm not telling you how many bacteria there are in the bottle. You can probably figure it out with the material we're going to learn today. But let's just suppose that after 60 minutes, the bottle is full. Now, I start with a new bottle. And this new bottle has 2 bacteria to begin with. Question, how long before the bottle is full? Okay, how long before it's full? Okay, so I hear 30 over here. 30 minutes, have as much time, okay? So that's the first answer you would think. This comes from thinking linearly. If you think about linear growth, you know, you take, if you take 60 minutes, we're starting with 1, you should take half as much time starting with 2. But let's think a little bit more. This is more like exponential growth. So who says something else, something different? Maybe 10 minutes, 20?
59.
I hear some crazy number, 59. How's that? What's that?
You're starting at minute 2.
You're starting at minute 2. That's right. That's a great way to put it. If, or let's say at time, let's say if before we had time 0, we started with 1 bacterium, and we went all the way to a full bottle at time 60, right? It's like you're starting at, let's say, time 1, right? 1 minute later. So we're starting at time 1 minute later. That means that it takes 59 minutes to fill up the bottle, right? That sounds very counterintuitive, right? Does it sound counterintuitive to you too? That it takes almost as much time to fill up the bottle when you start with twice as much the material? Okay, the reason for this counterintuitive behavior is that exponential functions are weird. They're fundamentally weird. And people have a hard time thinking about exponential growth. I think part of financial literature, being able to understand finance and the growth of compound interest, has to do with this intrinsic weirdness of the exponential function. If you put money in a retirement account, and that money makes, what, 10% a year, you think, well, that's nothing. I might as well just put that money somewhere else or party or whatever, and it's not going to make a much difference when I retire. You guys are not thinking of when you're going to retire anyways. It's too far away. I'm barely thinking about when I'm retiring. But the point is, when you retire, that 10% increase annually is going to blow up into a much larger amount than before. I don't know, 20 times more than before, or 30 times or more than before. It used to be even more because now the interest rates are not quite as high as before. but you're going to see the numbers, and you're going to see how a small interest annually can compound over the years and blow up into some really, really large numbers. So there you go. So let's start thinking about exponential growth. And we'll give you, as examples, we're going to talk about bacteria, we're going to talk about money, and we're going to talk about turkeys. There you go. So let's see. So if y of t is the population of bacteria, here's the main idea I would like you well, let's try and distill it together. What kind of idea would we like to use, could we use to describe the growth of bacteria? Okay. And the idea is something about the rate of growth. Okay? The rate of growth of bacteria. Does anybody like to say something about the rate of growth? Here's a hint. If I start out with twice as many bacteria, the rate of growth is how much higher than before?
It's the same.
No. Not the same? So let me put it like this. You start with one bottle of bacteria, and you measure how fast the bacteria are growing. Okay? Let's say that you're growing at, I don't know, suppose we have 1,000 bacteria. Forget about the one bacterium example. Suppose you have 1,000 bacteria in here, and you're growing at about 10 bacteria per second, let's say. Now you start with 2 bottles with 1,000 bacteria each. This bottle is growing at 1,000 bacteria per second. This other bottle is growing at, sorry, did I say 1,000? 10 bacteria per second. This other one is growing at 10 bacteria per second. So overall, the 2 of them are growing at 20 bacteria per second, right? So if I double the population, the rate of growth is doubling, right? Okay, that's the basic idea for exponential growth. If I double the population, the rate of growth is doubling. If I do 10 times the population, the rate of growth is 10 times as before. So in other words, the rate of growth is proportional to y, to the population itself. Let's think again. If I do twice as much y, then the rate of growth is twice as much as before. Okay? In mathematics and in physics, we say when something is proportional to something else, that's because the one thing, the y dt, is equal to a constant times y. Okay? That's what proportional means. It means that one is equal to a constant as the other. Okay, and that's the basic formula. The rate of change of the population is equal to a constant times the population itself. Okay, now let's think about a possible solution of this equation. This is called a differential equation because it involves a derivative. Never mind what it's called for now. Let's think about a function y of t satisfying this property right here. Can anybody tell me any function whose derivative satisfies this equation here? Yes? Y to the almost, y something like that, yes. You're thinking about a power function. Think more. What's the name of this section is what? Exponential growth, right? So it's going to be some kind of
1/2 ky squared plus constant.
1/2
Ky squared.
k to the y squared. No, let's think an easier function than that. That's right. E to the kt. So right now, I just heard a suggestion, e to the kt. This is exponential growth, and there's a k in there, okay? And the suggestion is that this function is a solution of this equation. What do I mean by that? It means that if I plug in the y dt here, and if I plug in y over here, the left side is equal to the right side. So let's test whether this equation is indeed a solution, whether this function is indeed a solution of this equation. So I'm going to write down dy dt. What is dy dt? Is the derivative of this thing. Now that we know the chain rule, we can actually compute this thing, right? Once again, the outer function is e to the t. The inner function is k times t. So the derivative of the outer function is e to the kt. But we need to multiply by the derivative of kt. And that's k. Okay? So the derivative of this function is e to the kt times k, and that is the same thing as y times k because this thing is just y. So as you can see, what the y dt is equal to k times y. So it satisfies the equation. Great. So, but there's actually other functions that satisfy the equation. This is not the only function that satisfies the equation. Can anybody tell me another function that satisfies this equation? Y of t equals, let me tell you, you can actually multiply this function by a constant, c times e to the kt. And it still satisfies the equation. So basically I'm rescaling that exponential function by a constant, okay? And I'm not going to do it because it's very easy. Same thing. You plug that function into that boxed equation. You plug in the derivative, plug in the function itself. Left-hand side is equal to the right-hand side. Okay? So this constant c, you can actually write a little bit more clearly. Let me just first write down what I just said. Also, this function is a solution of the boxed equation. Okay. So now let's think about the initial population. So if y of t is equal to constant times e to the kt, what would be y of 0? Just as an example. Okay? Let's think. This is time, right? Constant times e to the kt. So if time is equal to 0, then this is c times e to the k times 0. Right? So this is c times e to the k times 0. But e to the k times 0 is 1. And that means that c is equal to y of 0. And that means that we can write this function down as y of t equal to y of 0 times e to the kt. Okay. So this is the general solution of that equation. And in fact, that's the general formula for exponential growth. And as you'll see, exponential decay as well. Okay, so we just derived this formula. Now from now on, we're basically going to be using it. Okay, we already derived it, so let's remember it. I'm going to go back to this formula several times today, but it's basically the initial population multiplied by e to the kt, an exponentially growing expression, or an exponentially decreasing expression. Without going too much ahead of ourselves, how can I tell if this function e to the kt is growing or decreasing? What do you think? Over time.
Is k is bigger than 1 or smaller?
Bigger than k, bigger than?
1 or smaller than 1?
Not 1? Bigger than 0, that's right. If k is bigger than 0, this expression will actually be growing over time. If k is less than 0, this expression is going to be decreasing over time. Okay? So this is going to come naturally when you talk about different examples. So k bigger than 0 is exponential growth. And k less than 0 is exponential decay. I'm not going to dwell too much on the graphics of this. I generally like to graph things a lot. But let's just draw it once. When you have a constant k bigger than 0, you have this kind of behavior over time. And when k is less than 0, over time, you have this kind of behavior going to 0. Okay, let's do a few examples of this so that you understand better what I'm saying. So our first example will involve bacteria, just like we did a moment ago. Let's say, tell you what, I'm gonna already start talking about word problems so that we start practicing that. So a bacterial population of bacteria starts out with 1,000 bacteria, and it reaches 3,000 bacteria after 10 minutes. Okay, the question is to find out population after t minutes. In other words, find the general expression for the population over time and estimate the population at 100 minutes. Okay, so this is not quite as clean as we had before. We're not being told how long until it doubles. We are told that after 10 minutes, we have 3,000 bacteria. Okay, so, and this is going to be a general principle for modeling. If you look at this equation here, we're going to be using this equation, as we said before. How many parameters do you see here? How many things are unknown? Parameters. What is it? Okay, the original population is one of the unknowns, y0, right? Y of 0 is one of the unknowns. Time is an unknown. Okay, fine, time is unknown, but you know, time is the variable, right? So it's supposed to be unknown. You're not supposed to ever really know exactly what the time is. You can calculate it for different times. But there's another parameter. What parameter? K. Okay? So really, in this equation, there's two parameters we need to find out. Y of 0 and K. And for any of these problems, no matter what you're talking about, bacteria, radioactive decay, whatever, you want to find out those parameters. It practically doesn't matter what the problem says. You still pretty much always need to find out the formula in general. In other words, you need to find all those parameters, and then you do something with that formula. So step 1 is translate this into math. Step 2, find the parameter values. Step 3, solve whatever question you're being asked. It's actually very systematic. So let's write it like this. Turn into math. So how do we turn into math this text over here? Well, once again, y of t is the population of bacteria. Population of bacteria. And what do we know? What do we know about y? What is the information that, can we write that in an equation? Do we know the initial population, y of 0? Yeah, right? That's easy. So y of 0 is equal to 1,000. Okay, what else do we know? We know y of 10, right? Is equal to 3,000. Okay, and we would like to know the formula after t time, after t minutes. So we can already write that y of t is equal to 1,000 times e to the kt. This is because this thing is y of 0, and I am already told y of 0. So we only need to find the parameter k. So this is to find parameters. Find the parameters. We already know y of 0, and now let's try and find k. Okay? We already used this equation here, right? Y of 0 equals 1,000. That's when I plugged in 1,000 for y of 0. But we still need to find that, we still need to use that y of 10 is equal to 3,000. So how do we use the fact that y of 10 equal to 3,000? Okay? Well, let's write it. Y of 10 is equal to, according to this formula, is equal to 1,000 times e to the k times 10. Right? That's what it means, right? At any given time, the population is y of 0 e to the k times the time. So there you go. But we also know that this expression is equal to what?
3,000.
We also know that this is 3,000. So here's where we're using the fact that y of 10 is 3,000. Okay? Now, here suddenly we have an equation that only has k as our unknown. The only unknown is k. So we should be able to figure out k from this equation. You guys agree? Great. So let's try and find k from this expression. And it's going to be always the same story. So if once you understand how I do it now here, you can do it by yourselves anytime. So the first thing I'm going to do is I'm going to cancel out this 1,000 and this 3,000. Right? I'm going to cancel out 1,000 on both sides, and I get that e to the k times 10 is equal to 3. Okay, now we got that k all the way up in that exponent. We need to bring it down so that we can say k equals to so and so much. How do we bring down k from that exponent? What was that again? Natural log, that's right. We take natural log on both sides. So if this expression is equal to this expression, then the natural log of this is equal to the natural log of that. But what is the natural log of e to the something? It's a something, right? Remember that the natural log of e to the, and then I'm going to write my tree from before, is equal to the tree. Okay? Natural log of e to the anything is equal to anything. And that means that k times 10 is equal to the natural log of 3. Natural log of 3. Awesome. And now what? Well, we just divide by 10, right? So k is equal to natural log of 3 divided by 10. Fantastic. So now we know k. Okay, the expression for k generally is going to be a little bit messy, something like this. It's going to be hard to write it down in this expression, but just remember the fact that now you know k. Okay? So let's do it just because we're being asked to find a population after 10 minutes. Just to be very clear, but in general maybe you don't need to write it, but let's do it. So it's 1,000 times e to the natural log of 3 divided by 10 multiplied by t. That's the population after t time. Okay, so now what else are we being asked? And by the way, we already used this information, so we can check it if you want. It's already used. So now we want to estimate the population at 100 minutes. So at that point, you fire out a calculator, and you estimate the value of k, and we estimate the value of, we estimate the value of k, which is, I actually did this in my calculator, it's around 0.1099. If you want to actually know the value. That number is bigger than 0, right? It better be bigger than 0 because we're talking about population growth. Okay, so now y of 100, let's think about it. What do you think? If you started with 1,000 bacteria and after 10 minutes you reach 3,000, how many bacteria do you think you're going to get after 100 minutes? Okay, but roughly speaking, let's say you have 3,000. You think what, more than 10,000? After 100 minutes? Is it more than 10,000? Probably, right? Okay, is it more than 100,000? What do you think? Or is it maybe more like 500,000? 500,000? Yes, more? Okay, who says it's more than 500,000? Okay, you only like three hands. Let's see, so y of 100 is equal to 1,000 times e to the log 3 divided by 10 multiplied by 100. And this is equal to 1,000 e to the, I can cancel out the 10 down here. This is e to the log 3 multiplied by 10. You know what that is? You can plug it into your own calculator. It's 6. About 60 million. Okay, that's a lot. Okay, so much more than we actually estimated before. Okay, once again, the exponential growth surprises us by its magnitude. Once again, when you compound things many times over, you get much larger numbers than you expect. All right, do you guys have any questions? Let's do an example with exponential decay. Okay, exponential decay is going to be very similar, except that k is less than 0. So you have a exponentially or decreasing function. You have a mass of, say, some radioactive material at time 0, and the mass becomes smaller and smaller and smaller over time. The way this happens is that the radioactive material spontaneously divides, like the atoms spontaneously break down into two atoms that are smaller, right? And this happens with a certain probability. You never really know when a particular atom will split, but every once in a while they do. Okay? The math is exactly the same, but k is negative. So suppose that you start out with, well, let me write it down again as a formula, as in words. Let's see, a mass of 50 grams of plutonium is decaying exponentially and after 10 years, it has decayed to only 1 gram out of a starting volume of 50 grams, mass of 50 grams. Question, find out how long it takes to reach a mass half its original size. half its original size. Okay, here's the thing, because do you think that at least mathematically, this plutonium is ever going to disappear into nothing?
No.
No, right? Exponential decay means that you're always growing smaller and smaller as a mass, but you never reach zero. So the way that people talk about the speed of decay is by referring to the so-called half-life. Have you guys heard about half-life? Half-life? Okay. So the half-life of a radioactive chemical is the time that it takes to reach half its original size. Okay? So if the half-life is short, it means that it decays fast or slow. That's right. If the half-life is short, say 1 year, it means that after 1 year it reaches already half its size. If the half-life is 1,000 years, that means that it's a more stable compound that takes 1,000 years to decay to half its size. There are compounds that have a half-life of thousands of years. There are compounds that have a half-life of minutes or seconds. They're very unstable. You barely see them in nature because they decay right away. And I'm actually making up the half-life of plutonium here. I'm probably making a mistake, probably by several orders of magnitude, but let's do it. Okay, so how do we turn this thing into math? Well, once again, let's talk about y being the mass, right? And what are we being told? Y of 0 is 50, that's right. We don't write grams in math, we just write 50, and the units are in your head. And what else do we know? We are told after 10 years it has decayed to only 1 gram. Okay? That means that y of, what is this, y of 1? Y of 1 gram? No, right? Y of 10 years is equal to 1. Okay, very good. That means that we are implicitly in these formulas, we're counting this 50 and this 1 in grams, and the time is in years. Okay? So this is the information. This was the first part, the math, turning into math. Let's turn into math the question. How long it takes to reach a mass half its original size? How do we write it down as an equation? So let's call it T0 such that y of T0 is equal to, in this case, how much? 25, right? And the question is T0 equal to what? Okay, let's find T0 such that y of T0 is 25 grams. That is the question. Okay, so now we find the parameters. Again, it doesn't really matter what the question says. 99% of the cases, my bet is you still need to figure out the mass at time t in general. Okay, you need to figure out the general formula, and then you answer the question that you're being asked. In this case, to find the half-life of plutonium in this example. So y of 0 is already known, it's 50. Okay, now let's calculate y of t. So what we know so far is that this is y of 0 e to the kt. Presumably k is going to be negative. We don't know this. We need to calculate the value of k, but we know, we have a good idea that it should be negative. And we know that this is 50 times e to the kt. So there's still one parameter we don't know, and that's k, right? Great. So how do we find the parameter k from the information we're given? We already used this thing. What about this one here? Y of 10 equals 1. Right? We haven't used it. Let's use it. So y of 10 is equal to 50 times e to the k times 10. And that, we know, is equal to what? 1. Okay, as a matter of fact, we have an equation, 50e to the k times 10 equal to 1. We only don't know, in this whole equation, the only thing we don't know is k. So we should be able to figure out k, right? Great. So how do we figure out k? Well, let's divide on both sides by 50. So we get e to the k times 10 is equal to 1 over 50. And that means if I take the logarithm on both sides, it means that k times 10 is equal to the natural log of 1 over 50. Right? Now, just for simplifying things, this is not completely necessary, but I know from the formulas for logarithms that this is the same as the natural log of 1 minus the natural log of 50, right? And the natural log of 1 is what? Okay, so this log of 1 over 50 is minus log of 50. Okay, and that means that k is equal to minus log of 50 divided by 10. Okay? Awesome. You could, at this point, you could write the formula for the time, the population over time, or the mass over time. We're not being asked that, but you should be aware that now you know all the parameters. We figured out 2. And now 3 is answer the question. Now that we have the mass over time, we should be able to figure out the mass that it takes, the time that it takes to reach half the size. So, any ideas? Now that we have the formula for the mass over time, it's not very hard actually. You just need to think the right way. Yes?
Y of 25.
That's right. And then what? Okay. Let's start with y of 25. Wait. Sorry. Did you say y of 25?
Yeah.
No. No, because.
No, y of t equals 25.
Yeah, exactly. Y of t equals 25. That's right. So y of t0 is equal to 50 e to the k t 0, and that should be equal to 25. So then what? Okay, plug in k and solve for t0, right? Okay, so basically, I already know k. I don't want to write the value of k right here because it's a bit of a mess. But basically, be aware that in this whole equation, the only thing we don't know is t0. So we should be able to figure out t0, right? Great. So then let's figure out t0 in that equation, and that's the half-life. So if 50 e to the k0 is equal to 25, that means that e to the k t0 is equal to 1/2. I'm going to take the logarithm on both sides again, and I get k t0 is equal to log of 1/2, which is actually log of 1 minus log of 2 is equal to log of minus log of 2. Just to clean it up a little bit, this is equal to the minus logarithm of 2. Okay, now t0 is equal to minus log of 2 divided by k. But this we know what it is. K we know what it is. It's equal to minus log 2 divided by minus ln 50 divided by 10. Okay, and now dividing by a number is the same thing as multiplying by its inverse, right? By its, how do you call this? By its what? By its reciprocal. So this minus cancels out with that minus over here, and this is the same thing as log 2 multiplied by 10 over log 50. At that point, you fire out your calculator, unless you're in a midterm exam, in which case I'm not going to ask you that question. And this is roughly equal to 1.7 years. Okay, there you go. So that means that the half-life of plutonium, at least in this example, is about a little bit less than 2 years. By the way, you can figure this out with spectacular precision. You know, if you take a mass of plutonium and you measure it very, very precisely to several decimals of precision, you can predict with very, very much accuracy how much plutonium you're going to have after 10 years, okay, or after 100 years. And actually, that is the basis for dating things like archaeological artifacts using the so-called radiocarbon dating. Have you guys heard of this before? Okay, so the procedure for radiocarbon dating is very much what we just said. You first figure out the half-life of radiocarbon. Radiocarbon is basically a radioactive substance that shows up in the body of almost anything that's alive. You figure out the half-life of carbon, of radioactive carbon, and you look at a sample that's been sitting around the soil for some time, and you look at how much radiocarbon there is. Okay? You compare that with the expected amount that you would expect to have in that sample, right? And you say, well, actually, this sample should originally have 100 grams of radioactive carbon, let's say, and it only has 20, right? That means that it has decayed from 100 grams to 20, and from that, you can tell how much time has gone by since that thing has been sitting around in the soil. Okay, that's how it works. You figure out the y of 0, if you will, by comparing it with let's say you have an archaeologically old piece of tree that's been that's fossilized, okay? You look at a tree that's very similar but that's alive, you find out, okay, this piece of tree, the live tree has more or less 100 grams of this substance. This fossil only has 20 grams, so roughly speaking it decayed from 100 to 20, and because the radiocarbon has a half-life of, I don't know, 200 years, 500 years, then it means that the thing has been sitting around there for about 2,000 years, okay? And you can do this with a very high precision. Sorry. Okay, so there you go. We don't have much time left, but there's a whole bunch of other examples I wanted to tell you. Because we don't have time, I still want to mention this. The so-called law of cooling.
I thought you were going to say law of cow.
Law of cow, no. But you're almost right, because this is law of turkey. Okay, so suppose you have a turkey, right? And we're not right at Thanksgiving time, but almost. So you have a turkey, and you have a turkey in an oven.
You can draw.
I can draw? Well, not too well, but oh well. So you put this turkey in an oven, right? And the oven is really hot, and then you take it out of the oven. What do you think starts happening with the turkey?
Starts cooling.
It starts cooling down, right? So if T0 is the temperature in the room, and you start out with this presumably much higher temperature T at time 0, what do you think will happen to the temperature over time? It goes down, right? It becomes closer and closer to T0, right? Does it ever reach T0?
Yes.
Well, I mean, in theory not, because it's always cooling down, but never actually reaching it. In practice, the temperature of the room is going up and down, and sure, it's probably going to do it anyways, but in math, what you do is you say something like the temperature over time is equal to T0, okay, the temperature in the room, plus something that decays exponentially. Okay, this differential is becoming smaller and smaller over time. So it's T0 plus some constant times e to the kt, where k is presumably a negative number. By the way, we never checked that in here, but look in the radioactive example, k is minus logarithm of 50 divided by 10. That's negative, right? Just like we predicted. Okay, so the formula for the law of cooling, if you were given a problem in an exam involving a turkey or something like that, is basically the same as before, except that you're adding a constant. T of 0 plus constant times, T sub 0 plus constant times e to the kt. Okay, and that constant actually is not, notice that there's no T of 0 anymore. Okay, in fact, T of 0 is equal to T0 plus C times 1 is equal to T0 plus C. So that means that C is equal to T of 0 minus T0. No matter. Just think about this equation right here as the equation for a turkey that's cooling down. So if you were given things like something like the temperature at time 0, let's say 350 degrees, and you're given the room temperature T0 equal to, let's say, 70 degrees, you should be able to do things like, oh, okay, you need a piece of information additionally. Let's say that T of, I don't know, 5 minutes or 2 minutes is equal to, say, 300 degrees. You should be able to find a temperature over time. Okay? And you should be able to figure out other things like what is the temperature after such and such time, or find out how long it takes until the turkey reaches 100 degrees, something like that. Okay? And we were missing talking about compound interest. I really didn't have time for this, but I think this is a very interesting question. Next time we're going to talk about related rates, so we won't have time to talk about it, but I'm going to ask the TAs to talk about it in the discussion section.